So if we look at the these are the Navier-Stokes equations which we are solving, and in most of these cases, ये क्या हो रहा है मैम, ये मिट क्यों रहा है? In most of these cases, this rho times A term became 0. Now this left hand side is what we call as the inertial term. Now in some of the problems, while you may be given this approximation that inertial term is 0, or you may be given that acceleration of the particles is 0. So there, without thinking, whole of the left hand side of the Navier-Stokes equation, you will put that as 0. Now when that becomes 0 is actually something which we would have done had we done a full course on fluid mechanics, where we do an order of magnitude analysis of all these terms with respect to each other. And if the acceleration term happens to be small, then we can make the assumption that this is 0. Okay. So for your case, it may be a priori specified that inertia terms are 0 or acceleration is 0. In that case, don't bother about solving the left hand side. Just write all the terms together as 0. Okay. But in any case, if you come across a flow where acceleration is not 0, then obviously one of the terms here or more will not be 0. For example, if we have a circular flow with circular streamlines, so there we know V theta is there. If V theta is there, can acceleration be 0? If something is moving in a circle, we know the normal component of acceleration is not 0. So therefore, V theta will not be 0 in that case, or acceleration will not be 0, and you will see that there is one term in the acceleration which will not be 0. Okay. Now the other three terms are the pressure gradient, gravity, and the viscous term. So if this is 0, that means particles are not accelerating, and then either the pressure gradient is balancing the viscous term, or gravity is balancing the viscous term. That is what you will find in all these solutions. Okay. So now let's move to the second example, and which I want to do, and this is the one. A circular version of the channel flow problem, and which is flow in a long pipe caused by a pressure gradient. So if I look at the geometry of the flow, this is the first thing which you should try to see. There's a pipe of radius r and length L, in which we have flow in the axial direction. We choose the, ये assignments क्यों अदला बदली हो रही है, यहाँ ध्यान दो. We choose cylindrical coordinates, which is r theta z. So z is the axial direction, r is the radial direction, and theta would be the circular azimuthal direction. Okay, and here now, that means in general what is given to us is that velocity will be equal to VR ER. And if we look at the gravity vector, the gravity, see things like this, once they are given, you know you will need gravity, so you should be able to write them in vector form. One of the mistakes people do is treat vectors as scalar. This is what has happened in the quiz also. In quiz 6, you are asked to find the force. And many of you have just written it like a scalar, combined all the x and y components, whereas you should have written it as fx and fy, two different components. So vectors obviously have to be split up like this. So this is the gravity vector. So now here what is given to us, that we are given, so flow caused by pressure gradient, pipe walls are fixed, now again the last thing which I have given, these three, steady fully developed V theta is equal to 0. Now since we are inexperienced or we are looking at things, these again have been specified to you. In real life, if you were solving this problem, these assumptions you will have to make yourself. That flow is steady because the flow has been going on, things don't change. Fully developed because it's a long pipe, so maybe near the ends it is not fully developed, but otherwise velocity profile will not change with z. Now V theta is equal to 0 in this problem sort of comes because there is nothing causing V theta. Now what could have caused V theta here? If the pipe was spinning, suppose we had a spinning pipe, the same flow, but if the pipe was also spinning, then the boundary condition would have led to V theta not being 0. So we could not have made this assumption V theta is 0. But since there is nothing which is causing a movement in the theta direction, and now here of course flow is also axisymmetric because nothing changes with theta. So again that assumption you will have to think about it yourself. It may be given to you. Otherwise, if it is specified, write all the assumptions, then you will have to. Okay. So now we have to find the velocity profile. Okay. This is the problem. Possibly it may be done in the tutorial also, I'm not sure. So now we will start with the boundary conditions. Boundary conditions will be on which variables? On velocity and pressure. So which are the boundary conditions which we know? The first boundary condition, which is obviously given in the problem. See, when you look at the boundary condition, you don't look at the equations at all. Looking at the problem and the geometry and will give you these things. And they will be needed in the solution at each step to solve for the unknown constants. So the first thing we should always do is look for the boundary conditions. And as I said, if you use CFD, that means in a more complex problem, you have to solve it using numerical methods. The program will first ask you for the boundary conditions. So getting the right boundary conditions is something which is very important. So this is what we have for pressure. Now for velocity, what boundary condition do we have? What can you think of the boundary condition for velocity? V theta is 0 is already given to you in the problem. It may not have been 0 had the pipe been spinning. Then what would have been V theta if the pipe was spinning? At R is equal to capital R, V theta would have been omega times capital R. That is for a spinning pipe. Now for this one, what will be the boundary condition do we have? The only boundary condition we have is on the surface of the pipe. And since the wall is fixed, what is the boundary condition we have? So we have at R is equal to capital R, velocity is 0. Now if the pipe was being pulled axially, then at R is equal to R, Vz would have been equal to the pipe velocity. So there could have been different boundary conditions, but you look at the problem and try to get the boundary condition. Is this clear? Which means that R is equal to R, Vr is 0 and Vz is 0. Now, these two things follow from a fully developed flow. So this comes from the fact that the flow is fully developed, and this comes from steady. And here we also have another condition. From axisymmetric, we will get velocity is not a function of. Now the question you may ask is, what about pressure? And what we realize is that in gravity has a component in the theta direction. So therefore there will be a static variation of pressure with theta, because gravity vector acts along the theta direction also. So therefore partial P by partial theta is not 0. But if suppose it was a vertical pipe and gravity was only in the z direction, then partial P by partial theta would also have been 0. Okay. So now given these, we start looking at the equations. So as we do in all these problems, we start with the continuity equation. Now the continuity equation is, now again, you will need to bring or look at this sheet. You have to bring this sheet for your measures, only this sheet. And so the continuity equation, of course, here we'll also add we will say the flow is incompressible, or we may say constant property flow. Constant property will say mu is constant, rho is constant, so incompressible is implied. So now the continuity equation is Now, one of the students sent a mail to me, and I have written this equation wrong in lecture 23. I have written partial v theta by partial theta is partial v theta by partial r. Please correct that. Just look at the continuity equation. I have made an error in writing that equation. So you can correct that in lecture 23. So this is the continuity equation. Now, how do we simplify this? Are any of these terms 0? Batao. Theta is 0 because v theta is 0 or x is symmetry. Both of them lead to. What about partial vz by partial z? Is that 0 or not? Now, what we can do is, if before doing this, if I write Vr is a function of which variable? It turns out it's only a function of r. Because it's not a function of theta, it's not a function of z, it's not a function of t. Similarly, if I look at Vz, it's only a function of r. And pressure in this case turns out to be a function of r, theta, and z. It's not a function of time, but it will turn out to be a function because r and theta have a g component. So statics will vary. Z, obviously, there's a pressure difference. So it's a function of z. So now, given this, this is 0 and this is 0. So what I get from here is and I have also made it a total derivative. So I get d by dr of r Vr is 0. So r Vr is a constant and Vr is equal to k by r. And then I use the boundary condition at r is equal to capital R, Vr is 0. So this implies k is 0 so Vr is equal to 0 for all r. अगर आप लोग असाइनमेंट वगैरह में बहुत बिजी हो तो मे बी यू कैन फर्स्ट फिनिश इट आई वेट फॉर 5 मिनट्स कॉपी कर लो एक दूसरे से असाइनमेंट फिर क्लास पे ध्यान दो so we get Vr is 0. Now we have the three equations r, theta and z. Which equations do you think we should go for first? We should go for the two velocity components which we know are Vr and V theta, both are 0. So we should go for these equations first. And then we can go for the Z equation. Because what will happen is, from Vr and V theta equation, we will get some information about pressure. And that will help us find partial P by partial Z. So that is why we go for these equations. So if I look at the R equation, now this the R equation, when you look for it, now what you will get here is everything else will become 0, because here what in particular what I would, if you look at the R equation, there's a term rho multiplied by V theta square upon R. If V theta was not 0, this term would not have been 0. V theta square upon R. But all other terms, either because of fully developed flow or because of steady flow, all these, everything else on the left hand side will become 0. And this you will work out. Please check out from your this thing that these terms will be 0. And from here, when you work out, what you will get is pressure will turn out to be equal to when you equate, you will get it in this form. And this you can work it out. Now, so this is from the R and theta equations. And when you differentiate this expression for P, what it is going to give you is partial P by partial Z is only a function of Z. F prime, which is just a function of Z. This is what you are going to get from here. Now what we do is, we move to a Z equation where we have Vz is equal to Vz of R. Now, here let me write the full equation once. So this will become rho times this is the full equation, and when we start simplifying, we keep in mind Vz is only a function of R. So if Vz is only a function of R, this term will become 0. Vr was 0, so this term becomes 0. Now, क्या हो रहा है? So left hand side becomes 0, G sub Z is 0, and what happens in the viscous terms? Do all of them become 0 or does any term stay? Which of the terms on the last mu with mu becomes 0? Vz is a function only of R. So the theta and Z functionality, they will go away. So what I'm left with is mu upon R d by dr of R dvz by dr is equal to f prime of z. Okay. Now what we will do is, we will use the same argument, left hand side is a function of r, right hand side is a function of z. So that means each of these is a constant, and as before, we call this constant as p prime. Now, so we get d by dr So we just integrate it and we get it in this form. Now it turns out we have only one boundary condition on Vz. What is the boundary condition we have on Vz? At r is equal to capital R, Vz is 0. Okay. So now, how do we find the two constants? There are two constants, only one boundary condition. So here we use the argument at r is equal to 0, the flow is finite. V cannot be infinity. And this will imply that C1 is 0. Because C1 is multiplied by log R. At R is equal to 0, flow velocity cannot be infinite. So C1 will become 0 and then you can find C2. So this is how you solve a problem like this. So more examples are given to you and this you will do, and also I have given you a sheet of containing about 5 or 6 problems. Try them out, and there are different geometries, different type of boundary conditions. The solution of that I will put up today itself so that you can, if you get stuck for assignment 10, you can have a look at those solutions. The solutions are very sketchy, like not fully detailed solutions. You'll have to work out with the solutions, look at them, but at least they will give you the answers. Okay. So this is how we do exact solutions. And definitely you will expect 1 or 2 questions from exact solutions in the exam. Now, for the last topic which we will do, before we get that, once we get Vz, what are the different things, physical quantities we can find? From Vz, what physical quantities we will be able to get? Let's have a look at that. So, If we finally write the form of Vz, it will turn out to be equal to minus P prime upon 4 mu times capital R square minus small r square. So, one thing we can get is the flow rate. Flow rate will be what? It will be equal to integral from 0 to r Vz times 2 pi r dr. So, this will be equal to in terms of the pressure gradient, you can get the flow rate. And obviously, if the pressure gradient is higher, you will get a higher flow rate. So, this is what you find. So, we get the average velocity in terms of the pressure gradient. And the pressure drop delta P, this is equal to 8 mu L V prime upon R square. Now, the other thing we can find and which we need to find is what is the shear stress on the surface of the pipe. Now, which component of shear stress are we, and if we integrate that, we will get the full force which the flow is exerting on the pipe. Now, what component of shear stress are we talking of when I look at the pipe surface? Shear stress is tau, which are the two subscripts? Which is the direction of area on the surface of the pipe? R. And in which direction is the flow taking place? Z. So, the shear stress when we talk of is tau Rz. Now, tau Rz, once again, we go to our handout and find tau Rz in terms of velocity. In fact, the whole purpose of solving this problem is to find tau Rz, because that is what will give us how much force is being exerted on the pipe. Okay. So, tau Rz is equal to mu times, and I copy it from the handout. Now, in a general problem, both Vr and Vz will not be 0. And you will evaluate this at r is equal to r and integrate this. Now, in this particular problem, what is Vr? Vr is 0. So, in this particular problem, this becomes equal to 0 and tau Rz becomes equal to mu times partial Vz by partial r evaluated at r is equal to r, and this becomes equal to mu times P prime times r upon 2 mu. So, this is equal to P prime times r by 2. if I do, we have done integral flow analysis also. So if I do an integral flow analysis of flow in this pipe, let's try to see whether the results match or not. So here what I do is, I choose a control volume like this. 1 is my inlet, 2 is the outlet, and the horizontal line is the pipe surface. So now, integral flow analysis in the z direction will give me sum of forces in the z direction okay. And what happens to the first term here? The first term is 0 because we have steady flow and fixed control volume. What about the second term? Vz rho v dot nda. Now Vz has some profile. You have to integrate that. But what we find is the profile at 1 is exactly the same as profile at 2. Okay? And Vz in is the same, but rho v dot nda has a minus sign on 1 and has a plus sign on 2. So basically, what will this final answer be irrespective of the shape of the profile? This will give me a 0. For a fully developed flow, this will also be 0. Because Vz is same distribution at 1 and 2, and V dot n has opposite signs. So now what I get is, this gives me sum of Fz is equal to 0. Now, what are the forces which are acting? This is the control volume. On this side I have P1 times A. On this side it is P2 times A. And this force, this is tau Rz. If the shear stress is constant, then on the side, the force which is acting, and in fact on the pipe force it will be in the negative side. So therefore what I get is P1 minus P2 times A minus tau Rz into 2 pi RL is equal to 0. And what I get from here is P1 minus P2 by L कौन सी वाली फाइल थी मैम? एक मिनट. So this is what we get, and we get that tau Rz on the surface is equal to P prime times R by 2, which is what we also got from the differential analysis. So here we sort of show that both of these things lead to the same result. Now, since we have only about 1.5 lectures left, because Tuesday को भी तो class है हमारी. So then I can take some more examples in that class on Tuesday. What the last topic which I will teach, and I've decided to keep this topic simple. So I'm taking a topic which will be rather easy. You'll not have a tutorial on this. On this topic, you'll not be having a tutorial. So I will have to, I will solve the problems in the class. But in the workbook, problems regarding this are given, and it's a fairly straightforward topic. What I want you to take home from this is, you have all seen dimensional analysis in some form or the other in high school physics. But here, what we will show is how dimensional analysis can be used as a powerful tool in engineering analysis. And that is, so dimensional analysis, so it will be, this you will see will be a method to reduce the number and complexity of experimental variables particularly for people who are doing experiments, etc. You will find dimensional analysis is a very useful tool, and it is independent of the branch of engineering you are studying. For example, we could even use it in solid mechanics problems, not just in fluid mechanics problems. And what the basic crux here is, if a phenomena depends on n variables, then dimensional analysis will reduce the problem to n minus k variables, generally k being from 1 to 4. And as an example, suppose we talk of drag force on a cylinder. Let's call it as F. And if we say this is a function of density mu v and the diameter of the cylinder. So now, if you want to find the drag force as a function of diameter, then, and if you are doing experiments, suppose you want to tabulate all this data, then suppose you keep the fluid the same, you keep rho and mu constant, then what will happen is, you will carry out some experiments for V is equal to V1, for V is equal to V2, for V is equal to V3. For different velocities, you carry out these experiments and you measure them and you make some curve. Keep in mind, this is for one fluid. Now, suppose you want to do it for 100 fluids, then you will have to draw 100 such curves. That means each velocity means 5 or 10 experiments. and each fluid will mean repeating all those experiments. Now here, if I tell you that this translates to if f is a function of rho v d mu, can be rewritten in this form, that f divided by rho v square d square is just a function of rho v d upon mu. Now what do you have to do? All you have to do is you do a single experiment, maybe 10 times with different values of rho v d upon mu, and you plot this, and from here now you will get the same information which those thousands of, which hundreds of graphs containing so many v's were doing. So that is what dimensional analysis can do for you. So the benefits of these are very obvious, that we reduce the number of variables, then it will help in planning and optimizing the number of experiments. And the number of experiments, when I talk, it need not be physical experiments. They may also be computational experiments. Each time we run something on the computer, we take it for granted it is very easy. But some of these runs are very, very complex. So therefore they take hours of running on the computer. So, and see, they will help us in giving scaling laws. For example, if I say f upon rho v square d square is a function of rho v d upon mu. Now, what I do is, I have two different situations. Let's say, consider I have a cricket ball and a marble. So the diameters of the two are very different. If I take these two things and if I ensure, so take two different situations. Let's take an example of a cricket ball and a small circular bead. So I'm not talking of a marble, I'm talking of something very, very small. Now to find the drag on the cricket ball, I may be able to place sensors and find them very easily. But for a small circular bead, it may not be so easy. So then what I will do is, if rho v d upon mu for cricket ball I have to find the drag force on the circular bead. I know its situation. I know this circular bead is falling, is traveling in some fluid whose density is known, whose velocity is known. So that means I can find rho Vd upon mu. for the circular bead. So I equate that for rho Vd upon mu for the cricket ball. So cricket ball is traveling, let's say, in air. So I know rho and mu of air. I know the diameter of the cricket ball. So when I equate these two, what will I get? I will get the velocity of the cricket ball, with which the two right hand sides match. Then I will carry out the experiment with the cricket ball and calculate the drag force on the cricket ball. Once I calculate the drag force on the cricket ball, I will calculate F divided by rho V square D square for the cricket ball, which I can do because I know the V, I know the D. Then because F by rho V square D square is just a function of Reynolds number, and if these have been matched for the bead and the cricket ball, then F upon rho V square D square for the bead will be the same as F upon rho V square D square for the cricket ball. And therefore, I can find F for the bead. This is what we call as scaling. And actually, it turns out to be a very powerful tool which we can get so that we can solve for problems. And that is one thing what we do. For example, big cars, when you have to test drag force on the car, you can't always do it on the car. So you make a small model of the car and you test it in a wind tunnel, and you make the wind tunnel speed such that the speed in the real, this right hand side, whatever is the non-dimensional number, is the same for the wind tunnel as for the real case. Then you calculate the force on the model and then equate the left hand side for the model and for the real thing. And that is how then we can really do the scalings. So now if we have a dependent parameter Q1, Q1 is the dependent variable. It depends on n minus 1 independent variables. This can be written as G of if Q1 is a function of Q2, Q3 up to Qn, we can rewrite this as we take Q1 minus f of this is equal to 0. So then we can say this can be written as G of Q1 to Qn is equal to 0. So that means we have n parameters here. Now what the Buckingham Pi theorem does is, it says these n parameters can be rewritten, can be regrouped into n minus 1 dimensionless groups, and these are also called pi numbers or pi parameters, expressed as capital G of pi 1, pi 2 up to pi of n minus m is equal to 0. And or this we can write it as pi 1 is equal to G1 of pi 2 up to pi of n minus m. So this is the basic Buckingham pi theorem, that dimensional quantities can be expressed as a function of dimensionless groups, where the number of dimensionless groups will now be less. And the last thing, m is usually but not always equal to the number of minimum number of independent dimensions are required to specify the dimensions of the original n quantities. So initially there were n quantities, each quantity will have some dimensions. So the minimum independent dimensions. Now which are the dimensions we talk of typically? We talk of mass, length and time. Instead of mass, length and time, we could also talk of force, length and time. But we have to take independent dimensions. In certain problems where temperature is a variable, then we treat theta also as an independent dimension. If charge is a variable, we treat that also as a variable. So these are the typical dimensions we choose, and how we use that, I think, let me just, we'll do that in the next class. How to determine the pi groups, I will do it in the next class. I will take 1 or 2 examples, and in Tuesday I will solve more examples. So that is what. I have sent a note for re minor and re quiz. How many of you have are in, यहाँ पे कितने बच्चे हैं जिनको री माइनर या री क्विज की जरूरत है? Please talk to me after this. Only one, but many more have missed. तो क्लास वैसे ही नहीं आते, क्या री माइनर री क्विज लेंगे? Anyway, I'll discuss with you. बंद कर, ठीक है.